carboxy, CH-DQ-SERF, CH-SERF. These are all some of the names if you go and look into the literature. Like most of the chemists, you're all familiar with a certain two-dimensional techniques called COSI, NOSI, ROSI, HSQC, like that. Similarly, when we develop a NMR methodology, a new pulse sequence, a new experiment, we give a name for it. And these are all the pulse sequences, about 25 different pulse sequences have been designed by my group, and we have named like this accordingly. So each and every method gives rise to certain information. We use it to extract an information the way we want. So these are all the acronyms we have given. So today what I'm going to tell you is, I will concentrate on, for the interest of the chemistry group here, and also of course generally I will physics people too, because I'm going to cover a lot of other things. So here I am going to tell you how we can develop NMR methodologies to investigate an interesting phenomenon called intramolecular hydrogen bond, weak molecular interactions. If you have to see in some of the molecules how NMR methodologies can be utilized. Of course, most of you people know there's a conventional way of utilizing NMR spectroscopy in deriving this information. Okay, if that is done in a conventional way like everybody does, then there is no need of me. Then as an NMR spectroscopist, we have to find out a method where we can simplify and get the information in a easy and in a comfortable way. So that's what we are trying to do. And just to show you, these are some of the molecules of our interest. Of course, I don't know, these are all molecules which have been synthesized by my group's students. They're all chemists. I don't know how to synthesize these molecules. Basically, I'm a physicist. But nevertheless, the information content, how do we extract by NMR spectroscopy, I'm going to tell you today. Let us look at this molecule. These are all called benzanides. Look at this molecule. So now these are all the molecules which are of pharmaceutically important molecule, which are used as anti-inflammatory and antiviral agents. Very interesting thing here, if you look at it, I have marked X, Y, X prime, Y prime, Z like that. There are in each of these ring, in this phenyl ring, we have X, Y, Z. In this phenyl ring also, I have X, Y, Z with prime notation. Why did I do that? See, now what we did is, in these things, we have substituted halogens in these positions. And what type of halogens we have substituted and how we have done, series of molecules have been synthesized. The reason is molecules may be simple, but we want to develop NMR methodologies by using what is called unconventional technique or multiple quantum techniques to analyze the NMR spectrum. So this is what we have been trying to do. And there are a series of molecules, and I'm today concentrating only on 4 molecules like this and show you how complex it could be and what we can do as NMR spectroscopists to analyze this.
Slides, are you moving? Slides are not moving, sir?
It is moving. I'm moving here.
Oh, here, no, we are not. The slides are not
I'm seeing here. In my case, I'm actually moving.
No.
We are seeing the photos of your
Photos of your group only, contributors
only.
Only that.
No, I have already moved, sir.
Is it?
No, it's not coming, sir.
Now?
No, sir.
No, I'm actually moving.
You reshare it, sir. You
okay.
Close it
Okay,
and
I'll come
reshare
out
it.
and okay, I'll come out and then reshare it.
Yes, sir. Now visible, sir.
Now is it okay?
Yeah,
Yes,
now
sir.
it is visible.
Yes, sir.
Now I'm moving the slides.
Yes,
Yes,
sir.
sir.
Okay.
Yes,
so
sir.
of course, did you see this slide when I was
No,
explaining?
we didn't see.
No, come
we
once
didn't see
again,
anything.
come from starting, sir. Yeah. Next.
Okay.
Next
Let
slide.
me repeat from the beginning for the benefit of all of you. All right. So, but remember, my time starts now. Okay.
Yes.
Last 5
Yes.
minutes you don't count.
Yes, sir.
All right. So let me start with the unconventional NMR methodologies, what we do to address the challenging problems of chemical and pharmaceutical importance. These are the contributors, students of my group. Some of them are still there. Some of them have already moved out to different places, occupying different positions in both academia and industry. Some of them are already faculty there. So what I'm trying to say is our group effort is a collective effort is to address the challenging problems in the analysis of NMR spectra of molecules both in the solution state, oriented molecules, and also in the solid phase. So this is our effort always. And then when I say we are putting efforts to analyze what are the challenges we are facing. These are the challenges we are facing. First of all, high resolution, NMR spectroscopy. If you look at the NMR spectrum of even a small, simple molecule, which I'm going to show now, can be extremely complex in a small region of about, let us say, 0.2 ppm or 0.5 ppm, there could be overlap of number of P transitions. So to achieving the higher resolution and enhancing the sensitivity of NMR signal, the detection of NMR signal is very insensitive. We all know among all the spectroscopy in the molecular spectroscopy range, if you go from X-ray to NMR, NMR is the least sensitive technique, very, very least sensitive technique. So how to enhance the sensitivity so that you can acquire the data faster, and how to degenerate the transitions. If there is severe overlap, how do you do the unraveling of those things, and how do you simplify the analysis of the spectra? Or these are all some of the common challenges which we come across in every day. So this is the thing I am going to address today. When I have to address some of these challenges, what we do is we play with what is called spin physics. Of course, basically, you can consider NMR spectroscopy, a hardcore NMR spectroscopy, as I can equate myself to the Inspector General of Police. What police will do if they take hold of a criminal, they will torture him to reveal the truth, right? So that he has to tell the truth. Exactly. What we do is we will torture the nuclear spins. How do we do that? By play with pulse sequences, NMR pulse sequences, so that we can get the information of our interest. And this information, just like that, we don't get it. The way we want, in an orchestrated manner, we can extract the information. And that is why we develop number of NMR pulse sequences. And over the years, we have come out with a lot of pulse sequences like this. We have given different names like this, which is for all of you who are chemistry people who are present here, you're all familiar with the acronyms of NMR. If you go to the two-dimensional NMR spectroscopy, you can come across a number of acronyms, which you know, like J-Resolve, COSI, TOXI, HSQC, HMBC, like that. These are all well-known techniques for you. But in literature, if you go and see in the NMR, there are more than several hundreds and hundreds of pulse sequences have been designed by many stalwarts working in this area all across the globe. So our group, in the same way, have designed number of pulse sequences. We have got about more than 25 or 26 pulse sequences like this. Each of these pulse sequence is a new experiment which is designed. And this technique will provide me the information what I'm looking for in a given molecule. Of course, it's not for the applicable to that molecule alone. Once we design and test for a molecule, it is general. It can be applied to any molecule of your interest. So like that, we have developed a number of sequences. Today, I'm going to tell you how we have designed the sequences to extract the information in some of the molecules where we were interested in understanding the weak molecular interactions, especially the hydrogen bonds in some of the molecules like this, which have been synthesized in our group. And it is not just the hydrogen bond of conventional, what you people look for, like two center or three center hydrogen bond. Most interesting thing is we look at fluorinated molecules. I'll show you as we go ahead how we are going to utilize such molecules. Of course, I don't have to tell the chemistry audience here. Fluorine, if you say take the organic fluorine, it is known that organic fluorine will not accept the hydrogen bond. It itself is highly electronegative. But recently it has been shown by various workers and also from our groups, we have synthesized number of such molecules where we have demonstrated organic fluorine will participate in.
Our field ado.
So I'm now concentrating on the molecule like this. These are called benzonilides.
Group vidre sir.
So these are all called benzonilides.
He has not attended many of the sessions.
Shall I continue?
Yes, sir. Please continue.
Because somebody was talking, I stopped. Okay. So now if you look at this benzonylide molecule, you have X, Y, and Z have marked here, and also marked X, Y prime, and Z prime in this phenyl ring. And these benzonilides are the group of molecules which have a lot of potential importance in pharmaceutical industry. That's why we chose these molecules to study and understand weak molecular interactions present in that. And for that, we have synthesized large number of molecules. Okay, large number of molecules, so that, okay. And in each of these positions, we have varied X, Y, and Z, which is nothing but fluorine, chlorine, bromine, different types of atoms we substituted to study the interactions. Just to tell you what is our role as NMR spectroscopists, I have shown you the spectrum of this molecule, where X, Y, and Z are different substituents. Just if you look at this, I have numbered the protons here, and I have numbered the peaks here. I want you to focus on these regions. If you focus on these regions, look at it, there are 5 protons, aromatic protons, which comes in the range of 7 ppm, are overlapped here. The peaks of 5 different protons with lot of multiplicity pattern present in that, in a spectral region of 0.12 ppm. 0.12 ppm in 500 megahertz is nearly about 60 hertz. Remember, in 60 hertz, 5 proton peaks with lot of multiplicity are overlapped. Now the challenge is, how do you unravel this one? How do you resolve this peak and make the assignment of the peaks for individual protons? This is a real challenge. What we do is, for this to unravel and make the assignment, we adapted a technique called multiple quantum detection, followed by spin state selective detection. This is a new unconventional technique, which most of you people don't use it. All chemistry people, what you people do, in a conventional NMR spectroscopy, you come and give the sample for the operator and record the spectrum. You are going to get a spectrum. This is not multiple quantum. It is a single quantum spectrum. Whereas I don't want to detect that. I detect unconventional one, which is forbidden in NMR. These are all called forbidden transitions. So that's why I wanted to detect these things, and I'll show you how we can utilize this to derive the information. Okay. Now, for the benefit of the audience, I wanted to make it much simpler. The question is, what is multiple quantum transitions? Why do we use that? I'll tell you what is MQT now, but why do we use that? First of all, we are using it for what is called spin system filtering. What is a spin system? All the group of coupled nuclei, which are coupled among themselves, form what is called a spin system. In a given molecule, there could be many spin systems. We can separate out the spectrum corresponding to each spin system. That is called spin system filtering. I can do it experimentally. I can remove the redundancy. The single quantum NMR spectrum, what you can conventionally see, has more number of peaks than what is essential to extract the information. I'll tell you, for example, okay, maybe when I go ahead and in the next 1 or 2 slides, I will explain to you. And I want to get the relative signs of the couplings. See, for example, all of you are familiar with scalar coupling, where the polarization transfer takes place between 2 interacting spins mediated through covalent bond. But you know what is a scalar coupling, what is called J coupling. You know the magnitude of the J coupling, but that also has a sign. If I say the coupling between 2 protons is 10 hertz, is it plus 10 hertz or minus 10 hertz? We do not know, but there is a sign for it. The sign of convention comes because the way the 2 spins are oriented, the 2 interacting spins, whether they are oriented parallel or anti-parallel between them. So there is a big theory for that. Let us not go into the details of that. But remember, I need to know the sign of the coupling. In a simple, normal one-dimensional NMR spectrum, you will not be able to get the sign of the coupling. Please remember, conventional one-dimensional NMR spectrum is invariant with the sign of the coupling. If I take the spectrum, I change the sign of the coupling and record the spectrum again and give you, you will not see the difference at all. The spectrum remains invariant, whether the J coupling or the scalar coupling is positive or negative. But I need to determine the sign. It's very important. How do we do that? So that's why we use multiple quantum. And then we also do what is called the spin state selection. I'll tell you for the sake of chemistry, PhD students and juniors students, I consider a hypothetical molecule like this. Don't worry what is X and Y, some different substitutions. I'm looking at the CA3 peak. If I look at the CA3 peak, what type of NMR spectrum I'm going to get for CA3 group? All of you should be knowing. CA3 is going to be triplet of doublets. Why is it a triplet? The CH3 is a triplet because of CH2. Two equivalent protons are coupled to that. So 2Na plus 1 rule, as a consequence, is a triplet. Then each line of the triplet is going to be a doublet because of CH proton. As a consequence, if I look at the CH3 proton, I'm going to get a triplet of a doublet like that. But then what I'm going to do in the spin state selection is, why this triplet of a doublet is coming? Because there's an alpha and beta spin orientation, parallel and anti-parallel orientation with respect to the magnetic field for these coupled spins. Now can I get the spectrum corresponding to only beta orientation of the nuclear spins? Or can I get this spectrum corresponding to only alpha orientation of the spins? It means in a spectrum like this, can I get only beta components or can I get only alpha components? One way is I can separate out or I can individually detect. That's another beauty. In NMR, we can play with the nuclear spins to detect individually either the alpha component or beta component of the spin. You can do that. Then my job becomes very simple. I can measure this, I don't want to go to the details. When I do this is called spin state selection. I can measure the couplings very easily. Okay. And this is what we call a spin state selection, where high field and low field components of the multiplets can be unraveled, individually detected. And I combine, what I do is I design new pulse sequences to combine the spin state selection plus multiple quantum detection, where my job becomes very, very simple. And in very complex molecule, even a simple molecule, I can get the information which is not possible in a conventional NMR spectrum. Okay. Now, what is a single quantum? What is a multiple quantum? For example, you know the selection rule in NMR. The change in spin angular momentum between two energy states. For example, this is alpha state and the beta state. This is a plus, this is minus half, and this is plus half. If you take the difference between these two, this is plus 1 or minus 1. It can be both. Spin can go from alpha to beta, or it can come from beta to alpha. Both are allowed. This change of spin angular momentum, difference between these two, when it's plus 1 or minus 1, you are going to get a resonance. That is called single quantum transition. So remember, all conventional NMR spectra, what you people are seeing in a day-to-day life, when you record your spectrum, they are nothing but single quantum transition. They are allowed transitions. Whereas if I take delta M not equal to plus 1 or minus 1, they are not allowed. They are called multiple quantum transitions, also called forbidden transitions in NMR. You cannot detect that. There is no way you can detect it. But there is a lot of uses there if I detect that. Then now, what is a multiple quantum detection? The question of multiple quantum detection is a very simple logic. Look at this one. I have two nuclear spins I have taken, which are coupled. Remember one important condition, if you want to see the multiple quantum, the spins must be coupled. There must be interaction between them. Either it could be a scalar coupling or it could be a dipolar coupling, but there must be a coupling. In the absence of the coupling, you cannot detect multiple quantum. So I have taken two spins, which are, one is, let us say, what are the four possible orientations if you have two spins? It could be beta beta, alpha beta, beta alpha, and alpha alpha. There are four possible combinations. Now, single quantum, what it means is a spin of one spin can go from alpha to beta. That is allowed transition. Similarly, another one allowed, you can see like this. Also, if I go to the another coupled spin, this is also allowed. It can go from minus 1 to 0. It is a single quantum transition. This is also allowed. So these are all called single quantum transition. There is a very simple formula to find out how many transitions you can get if n spins are coupled. It is a simple combination. 2nc n minus 1 is there. If you can utilize that, you know that if I have 3 coupled spins, you'll get 15 peaks. If I have 4 peaks coupled, you get 56 peaks. We don't require all of them. They're all redundant. Excess number of transitions are there to derive the information. That is more peaks are there. We don't want them. So on the other hand, if I go to the double quantum or 0 quantum, what will happen? Now, this is the minus 1 plus G, this is plus 1. Minus 1 to plus 1, can I allow the spins both simultaneously come from beta to alpha or go from alpha to beta like this? It is not allowed. In NMR, it is not allowed, it is forbidden. Supposing if you detect, I will do some trick to detect, then what will happen? There's only one transition present here. Whereas single quantum we had 4 peaks. Okay, so that is the one advantage. Now the question is, you will simplify the spectrum. So what? What do I get out of it if I do the double quantum detection? Remember how the chemical shift and the J coupling evolve in a double quantum. It is like this. Look at this one. Now I have 2 spins, let us say A and M. Simultaneously, I allow them to undergo transition like this. That is from -1 to +1 or +1 to -1. This is called a double quantum. And I call this these 2 spins simultaneously undergoing transitions as active spins. And you can consider them as a super spin. Simultaneously, it is undergoing transition. It is called a super spin. And if there is any other spin which is not undergoing transition, we call it as a passive spin, or also called spectator spin. Remember that. So in this case, what is going to happen is, if I have a double quantum transition, what is going to happen? Simultaneously, A and M will undergo transition. As a consequence, in the double quantum, if I look at total chemical shift, it will be sum of chemical shift of A and sum of chemical shift of M. So in the double quantum dimension, you will get chemical shift of both of them together. But what about the coupling? You will not see the coupling there. I'll tell you by taking this example. That is a double quantum in a 2-spin case. Now what happens if I take the 3-spin case? Just to make you clear, look at this one, the same example. Now I'm flipping 2 spins simultaneously. I also have a 3rd spin here, which is watching it. This is called a passive spin. Passive spin is not undergoing flipping from alpha to beta or beta to alpha. So what does it mean? Generally, what you are going to observe in NMR spectrum is the coupling always between active spin to passive spin. Active spins will always couple to passive spin. That is what you are going to see. Now, in this situation, we can get the chemical shift of both of them together as a sum, and J coupling you are going to get simultaneously as a coupling between AX and MX together. Okay, so that means in the double quantum of this, we get only 1 peak. Okay, only 1 peak. Of course, because of the splitting, it is going to be a doublet. So that doublet separation gives me JAX plus JMX together. This is just to make you understand. Now, what happens to if I undergo transition between these 2 spins like this? This is some 0 quantum. This energy state is 0. Total spin angular momentum is 0. This is also 0. 0 to 0, I can also make the spins to undergo transition, which is conventionally forbidden again. I can do that. When I do this also, there's a biggest advantage. Similarly, compared to double quantum and 0 quantum, what happens is, in the case of double quantum, the chemical shift always come as a sum. In the case of 0 quantum, they come as a difference. That is the important point. Remember, and as a consequence, if I go to the 3-spin case like this, similarly, when I allow both the spins to undergo 2 spins to 0 quantum transition, I am going to get difference of the chemical shift, and I'm going to get difference of the J couplings. Very simple arithmetic. You have 2 equations, 2 unknowns. Very easy to get chemical shifts and J coupling. But the spectral complexity also gets reduced. I use this idea. For example, in my molecule of our interest, which I showed you in the beginning, I'll consider particularly only this group. Remember, I'm concentrating only on the 1 phenyl ring. If I take 1 phenyl ring and put it here, now what are the possible, how many protons are present here? I'm not worried about the fluorine now. I look only for the protons. I name them as A, M, P, and X. For the benefit of the chemistry people, students, please remember, whenever you see the NMR spectrum, why do you see the multiplicity? It is because of this. Let us consider this proton A. The proton A will allow it to undergo flipping from alpha to beta or beta to alpha. That is allowed transition single quantum. Then that is called an active spin, and these 3 are called passive spins. So in NMR spectrum, if you look at the chemical shift of A, we get the coupling between AM, AP, and AX. All the 3 you will get. So how many peaks do you expect then? A will become a doublet because of M, doublet of a doublet because of P, and doublet of a doublet because of X. So you will get 8 lines. A will, at the chemical shift of A, you get 8 lines. Okay, let us see what happened to M now. M also, if you undergo transition like this, M undergoes coupling between AM, MP, and MX. Again, you get 8 lines. Now extend the logic. There are 4 protons. So in each chemical shift of all the 4 protons, how many peaks you expect? You are going to expect 8 peaks in each chemical shift. Totally, this group alone gives me 32 peaks. That too without coupling to fluorine. Now I bring in the coupling to fluorine. It is going to be extremely complex. Remember, that's what I showed in one of the slides. In a chemical shift range of 0.2 ppm, you have so many peaks present. Like this, about the 64 peaks will be present. That is what you have to resolve now. That is a challenge. If you look at the one-dimensional spectrum, you will not be able to analyze it so easily. So what we do is, instead of with the fluorine coupling, when you have 64 transitions, I am going to now separate out the peaks for each ring. How do I do that? This is what is called spin system filtering, which I explained to you. Now what I'm going to do is, if I take the entire molecule like this, in the aromatic region, I must expect 128 transitions in the proton spectrum. How do I get 128 transitions? So difficult. Just now I explained to you. To understand that, what we will do is, let us see how I can distinguish between 2 spin states. Remember, I consider a molecule like this. What I will do is, if I look at the phenyl group, forget about the fluorine, I'll use a trick. I'll make sure that all 4 protons simultaneously undergo transition from A to M, or plus alpha to beta, beta to alpha, like that. If I take all the 4 protons in the beta beta state here, this is minus of, minus of, minus of, minus of, turns out to be minus 2. This is plus of, plus of, plus of, turns out to be plus 2. So this transition, minus 2 to plus 2, the change in the spin angular moment or the magnetic moment between these 2 energy states is 4. This is not allowed. It is when they change in the spin angular momentum, or I would say magnetic energy for each energy state, if I find out the difference, if it is only plus 1 or minus 1 is allowed. Now it is plus 4 or minus 4. This is called 4th quantum. If I do 4th quantum in this case, what is going to happen? That is our challenge. We will do that. What I'm going to do is, I'll take these 2 spin system. In NMR jargon, we call it as AFMP spin system. This is AFMP and this is X nuclei. This is similarly AMF. There are 2 such type of 5 coupled spin systems in the molecule. This, if you look at the molecule, if you know NMR, you can easily say there are 2 different coupled spin systems here. The reason is, this and this is not coupled. There is no interaction of any of the protons or any of the fluorine between this ring or this ring. There is no interaction at all. They are isolated spin systems. So there are 2 isolated spin systems here. That is the idea which we are going to capture. And when I do that, I can do the first order analysis very, very easily. So what I will do is, I start detecting the 4th quantum transition, which are forbidden, in an indirect way. How do I do that? By using what is called 2-dimensional technique. A technique that we can design. This is a pulse sequence. This is not pulse sequence designed by our group. This is a well-known sequence. I'll tell you how we have designed the sequence in this unconventional technique. This is called heteronuclear multiple quantum, which is a well-known experiment. When we do that, without going into the details, I can achieve spin state selection. What do you mean by a spin state selection? When I simultaneously detect 4th quantum in this molecule, for example, this fluorine, I'm leaving it untouched. I don't touch fluorine at all, both in the T1 dimension or in the T2 dimension. Or in other words, both in the single quantum dimension or the 4th quantum dimension, I'm not touching fluorine at all. That means the spin state of the fluorine remains same. Alpha of the spin remains, of the fluorine remains alpha, beta of fluorine remains beta. So that is called spin state selection. I can achieve it. When I do that, very easily, I'm going to get a spectrum like this. It's a beauty. Look at this one. This is a 4th quantum dimension. This is a single quantum dimension. This is our 4th quantum single quantum correlation experiment. Now, very interestingly, what will happen? When all the 4 protons are flipped at a time together, what I'm going to get is a peak at the sum of chemical shift of all the 4 protons here. This is for this ring, and this peak is for this ring. Fantastic. I must get only 1 peak. But remember, fluorine is present as a passive spin. Now, there is always a coupling between active spin and passive spin. As a consequence, this compound spin or super spin, all four together, is coupled to fluorine. That's the reason why in the fourth quantum dimension, it will become a doublet. So what is this doublet going to give me? This doublet separation is going to give me some of the chemical coupling between all the four protons with fluorine. So I can now remember the beauty is these two are getting separated out in this fourth quantum dimension because the proton chemical shift of these four is entirely different between the proton chemical shifts of these four when you take as a sum, when you take them as a sum together. As a consequence, I can separate out of this ring protons and this ring protons. Very easily I can separate out the peaks. And this is the one-dimensional spectrum. Look at it. You cannot identify from this one-dimensional spectrum peaks pertaining to this phenyl ring or the peaks pertaining to this phenyl ring. It's a very complex molecule to analyze. Now in my experiment, I can separate out these two ring systems. Then you ask me, what do I get out of it? Now I go and take the chemical. If I take the cross section along this axis, I can get one-dimensional spectrum corresponding to this. And if I take the cross section of this, I get the one-dimensional spectrum corresponding to this proton. That's fantastic. I can separate out this. Another interesting thing, if you observe, if you look at it, these two peaks appear tilted like this. If you carefully see, similarly, some of these peaks here appear tilted in this direction. If I take the slope of the displacement of these vectors in two cross sections, this is a positive slope, this is a negative slope. Fantastic. This will tell me this separation gives me J coupling, and then this tells me this J coupling is, if it is positive, this J coupling has to be negative relatively. So I can get the sign of the coupling, which is not possible to get from this spectrum at all. From this spectrum, if I give you can never get the sign of the coupling. Whereas from this experiment, you can get the relative signs of the J coupling also. That's one thing. So now, with this, after simplification, very interesting thing I'm going to show you. Now I'm looking at the NH proton here. I was not looking at this so far. Now look at this NH proton in this molecule. This looks like a partially resolved doublet. Fantastic. Why it is a doublet? How can it be? See, remember, this fluorine to this proton coupling is impossible because 1, 2, 3, 4, 5 bonds away. 5-bond fluorine proton coupling is known to be negligible, less than 0.5 hertz, which you cannot detect because of even the natural line width. In which case, how can this be a doublet of 16 hertz separation? Similarly, if you look at this fluorine also, this 4-bond coupling is not possible, it is invisible. But then how can we get 16 hertz? This is where our real experiment and real spin physics starts. To understand this, I know this is quite unlikely, 4-bond, 5-bond fluorine proton or proton-proton coupling. So what we did is, the simplest way is chemistry way. What we do is, you remember in this case, the fluorine is here and fluorine is here. So what we did is, we synthesized the molecules. And of course, before that, I wanted to know why it is a doublet. Why not two different peaks? One may ask a question, there could be two different molecules. They may get individual peaks. To do that, you do the fluorine decoupling while detecting the proton. This becomes a singlet. When I break the coupling between proton and fluorine, this is a singlet. This tells me there is an interaction between fluorine and proton, NH proton and fluorine. Although this long-range 5-bond coupling is supposed to be 0 or negligibly small. So what we do is, look at the fluorine spectrum again. This is proton spectrum. To double confirm, you look at the fluorine resonance. In this fluorine, we should expect 32 peaks here. Okay, if I look at this now, I'm looking at the X part of 6 coupled spin systems. 6 spin system and they are coupled, we must get 792 peaks in principle. In the fluorine part itself, I must get 32 peaks here. I am observing 16, doesn't matter, some of them are not visible. And when I do the decoupling of this proton while observing fluorine, again it is becoming a singlet. Both this experiment tells me there is a coupling between fluorine and proton. You cannot just ignore it. It is not just a simple doublet. But at the same time, this coupling strength is quite large. So what we did is, the question comes, if this fluorine is coupled or this fluorine, which is coupled to that? If this is coupled to this is a doublet, I understand. If this is coupled to this, it's a doublet, I understand. If both the fluorines are coupled to NH proton, then it must be doublet of a doublet. It must be a 4-line pattern. We are seeing only 2 lines. Now question is which fluorine is coupled. So for that, what we did is we removed the fluorine from this position, moved to this position in the molecule. When you record the NMR spectrum, NH peak is still a doublet. That shows there is an interaction of this fluorine with this proton. And we have ruled out temporarily right now, this fluorine is not, when it was here, was not coupled to NH proton. That is one of the conclusion. Okay, how are you sure? What we'll do is, we moved the position of this fluorine from this position, we moved it here. Now, there is no doublet at all. And we, at the same time, we brought back the fluorine to this position from here. That tells me this is the fluorine when it was here, was interacting with the NH proton. This tells me when fluorine is here, there is no interaction with NH proton. Okay? This is a very simple way of understanding in a chemistry way by synthesizing the molecule. Okay, so now this is not enough. What we do is, if NH peak, if it is confirmed this is to be a doublet, why it is such a large coupling? Then the question is, such a large coupling when it is not possible, 5-bond coupling, what is the mode of magnetization transfer? How can the magnetization between this fluorine to this proton gets transferred? When the polarization transfer has to take between 2 interacting spins in NMR, there must be a medium. The medium is a covalent bond. When I say there is no covalent bond, how can there be an interaction? Okay, there is a possibility we get what is called the non-covalent interaction in NMR. I don't know how many chemistry people here, chemistry students know. In a molecule like this, when it is separated with so many bonds, proton and fluorine here, there is an interaction of 8.3 bonds, which is not going through covalent bond. This is called non-covalent bond scalar coupling in NMR. This can happen in some special cases when their van der Waals radii are very close and they're overlapping. Don't worry about more details. But now the question is, when that is the situation, is there a transmission of spin polarization between fluorine and proton through hydrogen bond? That is our next question. If that is case, if there's a magnetization transfer is going on between fluorine and proton through hydrogen bond, next question is, how can fluorine accept hydrogen bond? Fluorine is very well known to all of you chemists. Fluorine cannot accept hydrogen bond. Then how do you understand that? But another thing is, if you look at the peak has 16 hertz, but it is partially resolved. It is not completely resolved. I do the deconvolution by mathematics. I do the deconvolution of NH peaks and measure the line width. It is exactly 16 hertz. Separation is 16 hertz. Line width is also 16 hertz. How can it happen? So now the doubt is, there must be an unresolved 14-9 proton coupling could be present. Also, that broadening comes because of nitrogen 14 quadrupolar relaxation. N14 is a spin 1 nuclei, it is a quadrupolar spin. It undergoes fast relaxation because its resident time in the excited state is very short. As a consequence, that can give rise to broadening. Okay, to understand that, what we did is, I took this molecule with the fluorine present here. This is a conventional proton spectrum. We got 16 hertz coupling. I did the N14 decoupling. Fantastic spectrum you got. You see, now this became a clear doublet here after N14 decoupling. That tells me there was an interaction of N14 with this proton. In addition to fluorine coupling, there is also interaction of this. So that is what. Now the next question is, we took this molecule to see what is happening. When I took this molecule, now instead of doublet, I am going to get doublet of a doublet. What does it tell me? It tells me not only this fluorine is interacting, even this fluorine is also coupled to this NH proton, which was not possible to see in a one-dimensional simple spectrum. Now, because it is significantly broadened due to N14 coupling, there is a J coupling of the N14 with this proton in addition to this fluorine. As a consequence, we were not seeing this FH coupling at all. But now in our experiment, when I did the N14 decoupling, I get doublet of doublet. One separation gives me J coupling between this and this. Other separation gives me J coupling between this and this. So very beautifully, I can see this one. Now, another thing is, why it is so broad? This is because of fast relaxation, I said. We call this in NMR jargon as self-decoupling. The fins are called relaxation decoupled. We call this as relaxation decoupling, not because of any radiation like conventional decoupling people do. Nuclei themselves decouple by relaxation. This is called self-decoupling in NMR. Though to understand that, what we did is, if it is self-decoupling, I want to arrest the motion of the molecule. I went to 230K. Beautifully, you can see now, this peak became a clear doublet of a doublet with a beautiful resolution. There is an 8-fold reduction in the line width here. Now I can clearly measure coupling between this and this and this and this. Now I know there is a mode of transfer of magnetization between fluorine to proton and this fluorine to proton through hydrogen bond, which I can very clearly understand. There are a number of other NMR experiments to show that. Okay. Now another interesting thing is we have to get the relative sign of the coupling. If that is very important in understanding the hydrogen bond. Now consider a molecule like this. For example, CEF, H and N. Here carbon 13 is NMR active, fluorine is NMR active, proton, and nitrogen 15 is NMR active. All four are NMR active. Okay, forget nitrogen 15 natural abundance, I'll ignore. But then 3 are NMR active. In which case, when I detect any one of the nuclei, I told you earlier, we get the coupling between the active spin and the passive spin. The detected spin is called an active spin. Non-detected spins are called passive spins. And you get the coupling between active and passive spins. So that means if I have to get all the couplings of the 3 nuclei, I need to do more number of experiments. I have to do carbon NMR, fluorine NMR, proton NMR, or nitrogen NMR. Instead, what I'm going to do is, again, our proposition is I will detect the forbidden transitions. I do double quantum, single quantum, zero quantum, single quantum transition between nitrogen and proton. Remember, this is the most difficult experiment to do because nitrogen 15 is present in natural abundance, 0.37% abundance compared to proton, which is 100%. A very challenging experiment. We can do that. So again, like this, I observe double quantum. And when I do this experiment, very interesting thing happens in this molecule. If I take an example like this, I'll take when nitrogen 15 and this proton, if I flip at a time, when I take the double quantum of this and this are passive spins. Okay. Another possibility, I can take this nitrogen and this proton. These two are double quantum I can do. Then these two are passive spins. So I can do an experiment simultaneously. I can get two double quantum of two spins together like this. Don't worry about the interpretation of these things. It's a bit of NMR. You have to understand. You must be a real expert in NMR. But nevertheless, I get this information. But what I want you to understand is the separation here. I'll tell you more about it in next slide. This separation is very, very interesting thing. This separation gives you some of the couplings like this between two protons and a proton and fluorine together. I get this one. Here I get NH proton and NF coupling together. Okay, now I know with my knowledge of double quantum everything, I try to interpret and then get all these things and sign of the couplings like this. Because the two equations are two unknowns, I get even the sign of the coupling. In this case, these two are opposite. It is not, there is something wrong there. Because when I fit it into the unknown hydrogen bond curves published by another group, all the couplings have to follow here. But in our case, it is following here. That means the couplings are either enormously large, it has to be, or it is not forming a hydrogen bond. In which case, we are unable to understand our results. So this is not possible. This tells me my sign of the coupling is absolutely wrong. With my sign of the coupling, if it is opposite, I fit in here. If it is the same sign, I should fit here. Then that means the way I determine the sign of the coupling is absolutely wrong. My sign of the coupling is not right. Then what does it mean? My experiment cannot be wrong, but the sign of the coupling is wrong. Why it is happening? So if I fit it into that, I do not get the hydrogen bond geometry. It doesn't agree, and it tells me there is no hydrogen bond. So there is a conflict now. We cannot understand the splitting pattern. We do not know the mode of polarization transfer. At the same time, my sign of the coupling is wrong. So what we did is we go to zero quantum excitation instead of double quantum. We did like this, and this is an experiment. This is where I wanted to tell you, look at the separation here. Compared to previous one, this is enhanced here. What did they say? In the double quantum dimension, always J couplings will add up. In the zero quantum dimension, J coupling will be difference of the, there will be a difference between the J couplings. But when there is a difference, why it will add up? This can happen only when one of the sign of the coupling is negative. So I'm right. My determination sign of the coupling is 100% correct. Whether I do zero quantum and double quantum, when I interpret the sign of the coupling, what I measured from my NMR experiment is perfect. Then why does it not agree with the hydrogen bond geometry? The real problem comes is this: most of you chemistry students, especially students who are beginners and research scholars, please understand. When I do nitrogen 15, when I detect nitrogen 15 has a negative magnetic moment. So what it means is, if the proton spins in a clockwise direction, nitrogen predecessors in an anti-clockwise direction in a magnetic field because of negative magnetic moment. So what you understand from this is, if I do nitrogen 15 and proton multiple quantum, double quantum behaves as zero quantum because these two are precessing in the opposite dimension, opposite directions. As a consequence, instead of adding up, they're subtracting. In the zero quantum, instead of subtracting, they're adding up. So this is the beauty. So if you are an NMR spectroscopist, you will understand. So now we know that double quantum behaves as a zero quantum and zero quantum behaves as a double quantum in this nitrogen 15 and proton experiment. Now using that logic, I interchange the spectrum, interpret the double quantum spectrum as zero quantum and vice versa, and get the sign of the coupling. Perfect, everything agreed, and it calculation agrees with our theoretical prediction and agrees with the hydrogen bond geometry. And my experiment confirms there is an evidence for the hydrogen bond with organic fluorine. By using unconventional detection of NMR spectroscopy, unconventional detection of multiple quantum, you are able to establish the sign of the coupling and also establish the presence of the hydrogen bond. Okay, so am I having some another 5 or 10 minutes, or should I stop? Hello? Hello?
Sir,
Hello?
please have another 5 minutes, sir.
Yes, sir. Yes, sir.
Okay, another 10 minutes is okay?
Okay, between 5 to 10 at
Yes.
the earliest.
Okay, I will try to finish it within 5 or 10 minutes because this is a very interesting thing which I want to show you how we develop the method in a canonical. So I will look at the weekly dipolar coupled spin system, how I will enhance the resolution. This is again a pharmaceutical importance. What we do in your chemistry, you do what is called enantiomeric discrimination. If I take the NMR spectrum of two enantiomers, it is indistinguishable. NMR is blind to distinguish enantiomers. If you take a one-dimensional NMR spectrum, I'll take R and S NMR spectrum individually and give you will not find any difference at all. NMR spectrum is indistinguishable. But now we have a different way of detecting. By some other way, we approach bidirectional approach. We have a classical approach by putting it in a chiral solvating agent or a derivating agent. We convert enantiomers to diastereomers, and we are going to do that. There's a way, but I'm not going to tell you about that. There, if we have published several, more than 30 or 40 papers, you can see that, you will know how we use that. But what I'm going to show you is in a chiral aligning medium, what we do. How does NMR spectrum differ in a chiral orienting medium? I want to show you. This is very interesting. Take an example of a molecule like this, any simple molecule. If I take the chemical shift of R and S, in the isotropic medium, you will not distinguish. You don't know what is chemical shift of R, what is S. Whereas, if I put it in a chiral anisotropic medium, chemical shift of R and S gets separated out. Same way, I can take the dipolar coupled system or a quadrupolar coupled system, then I can, in a isotropic, hello? In a conventional way, you will not be able to separate these two. Whereas in a chiral anisotropic medium, I can separate it R and SP. I use this logic. Now look at this molecule. It is a weakly dipolar coupled system. It is a very, very complex spectrum. And quickly I'll show you how our NMR methodology you can utilize to solve this one. Now I'm looking at this CH3 peak. If I ask the question to any of the chemistry students, how many peaks are there here? They can easily say there are about 78 peaks. In reality, theoretically, there must be 48 peaks present there. Where are you seeing 48 peaks here? You're not seeing 48 peaks. You're not resolving, but we have to resolve that. First, to understand that, we should understand spin physics. Let us see why it is so complex. What makes it so 48 peaks? Look at the CH3 peak here. In the NMR jargon, we call it A3 MPX spin system. CH3 should be single peak in isotropic. Whereas, if I put it in an aligning medium, it is going to be a triplet because there's a dipolar coupling between protons. And then If this CA3 is coupled to M, then because of alpha and beta spin states of M, it is going to be a doublet. It is further coupled to P, this proton. Then again, because of the alpha and B states of P, it is going to be doublet of doublet. Now it is also coupled to X. Then it will become doublet of doublet of doublet. It is going to be 8-line pattern. Okay, I am concentrating only on the middle peak. What about other two peaks? They also become 8 lines each. So how many peaks you got? 24 peaks you got. This is for one enantiomer. If both the enantiomers are present, another 24 peaks. When R and S both are present, you have 48 peaks present in the CA3 peak alone. That is why it is so complex, you are not able to resolve. But what we do is, we do again what is called the double quantum excitation of this one. We can have double quantum excitation of 1, 2, 1, 3, or 2, 3, all the three possible. And in this case, each time we get a doublet because of the passive spin coupling, and they are indistinguishable. Doesn't matter. I use this logic, and this is a new experiment we have designed. And then we get a beautiful spectrum like this. This is a very well-known selective refocusing experiment. In our experiment, what we do here, this molecule, if you look at it, can you see here, this peak, so many peaks which are overlapped here, I can resolve in the multiple quantum dimension. This is called a double quantum dimension. I take the cross section here, I get 6 peaks, very easily I can analyze. This is a simple molecule. Now we go to the realistic excitation of this molecule. This is what I wanted to show you. The CA3 coupled to other protons, simultaneously when you excite this one, then we are going to see the marks which are given, like filled circles and open circles, identify R and S for me. What I have done here is I have gone to triple quantum excitation. The triple quantum excitation makes me all the 3 protons of CA3 which are dipolar coupled as a compound spin, as a super spin. It will see its coupling to other spins, and this is the beauty. Okay, so this is the 3 CA3 protons coupled to 2 protons. If you look at this one, there are 24 peaks here. I'm sure you will not be able to resolve it in a one-dimensional way, but in our two-dimensional way, all 24 peaks we could identify. In that, out of 24, 20 we have easily identified for R and S. This is also simple. It's not a complex molecule for us, but the real complexity comes here. This is a realistic system, what I explained to you just now. I'm looking at the CA3 peak here. What did I say? There must be 48 peaks here. Where are 48 peaks here? But look at it in my triple quantum, single quantum correlation experiment. Here 3 peaks, 3 peaks, 3 peaks, like that. There are 8 cross sections here. Each cross section you get 3 peaks. You identify all 24 peaks here for R, 24 for S. All 48 peaks we are able to identify. This is a fantastic methodology we developed, okay, for analyzing simple spectra for what is called for getting enantiomeric discrimination of the molecule. This way, what is not possible in isotropic conventional NMR spectrum or distinguishing enantiomers R and S, you are able to distinguish by using the thicker crystalline medium in a partial aligning medium. But the partial aligning medium is a problem of resolution. We cannot resolve all the peaks. But then we bring in our method by a multiple quantum detection, we are able to observe all the 40. This is where, look at this one. Can you say, believe me if I say I have 48 peaks here? This is the one-dimensional spectrum. If I say there are only 3 or 4 humps are there, nothing. But look at my spectrum here. All 48 peaks we are able to resolve. This is the beauty. And of course, I don't want to go more into the details. And I just want to show you one spectrum like this. This is one of the methods which we developed. Same molecule. I am going to show you here what I have highlighted in a broken rectangle. I have expanded here. And this is where we must get 48 peaks. If you are counting, you will see only 5 or 6 peaks in the one-dimensional spectrum. But in my spectrum, here is, if you just look at this one, if I say there are 16 peaks here, do you believe me? This is 4 peaks, 1, 3, 3, 1 quadrant, 4 peaks, 1, 3, 3, 1 quadrant, 1, 3, 3, 1 quadrant, and 1, 3, 3, 1 quadrant. There are 16 peaks hidden here, which you are able to resolve here. Like this, we can develop number of pulse sequences. This is again the unconventional technique, not a conventional way of NMR. We go and detect the forbidden transitions. what is not allowed, and use it for our advantage. But how we detect the forbidden transition is more of a involvement. You must be an NMR spectroscopist for it. I cannot explain to you. Here, all 48 peaks have resolved, and I am able to resolve the peaks separated by 0.2 hertz. It's impossible. Here, look at it. Line width itself is about 10 to 15 hertz, but I am able to resolve 0.2 hertz peak separation. So what I'm trying to say is, if you understand the logic, there are ways to solve it. We have a number of problems like this. What we do is we understand spin physics and develop new NMR experiments and address the challenges. So our idea is there are always hurdles in front of us. We have big walls, but we break the barriers. When you break the barriers, what we are going to see? A ray of light at the end of the tunnel. Always in our experiment, we have designed so many pulse sequences to combat the challenges, and every experiment, we are seeing the ray at the end of the tunnel. So we are successful in solving many of the challenging problems. With this, I'm going to stop. I will thank the audience for giving me an opportunity to speak to you. Thank you very much.
Thank you, sir. If time permits, can we take one question?
You can take 10 questions, no problem.
Okay, sir. So does alpha and beta corresponds to Pauli spin states? How to calculate the multiplicity?
No, not Pauli spin states. It is the spin orientation of two spins in the direction of the field, in the direction opposite to the magnetic field.
How to calculate the multiplicity of factor M?
What factor M means?
So it was in relation to the question I asked, that alpha and beta correspond to Pauli spin state. How to calculate the multiplicity factor M?
Okay, the multiplicity is always given by 2nc n minus 1. Okay, if n is the number of coupled spins, let us say n is 3 spins are coupled. 2 into n is 6. 6c n minus 1 is 2. What is 62? If you take the factorial, it turns out to be 15. So there are total number of peaks you expect is 15. Okay. Now go to the each proton. Let us take 3 protons are coupled. Proton 1 is coupled to remaining 2. Okay. Then it is at the site of this proton, 2 protons are coupled. It should give rise to 4 peaks. 4 plus 4 plus 4, it should be 12 peaks. But in 3 spins are coupled, we get 15 peaks. You may ask me a question, where are the 3 peaks coming from? It is a combination transition which requires more theory of NMR, you don't worry. But remember the formula, 2nc n minus n is the one formula which tells you number of peaks which are detected, number of multiplicity pattern, how many peaks are available. Okay. And again, it depends upon chemical equivalence and chemical inequivalence. With chemical equivalence, we all follow what is called a Pascal triangle. It is nothing but the coefficients of the binomial expansion. If they are non-equivalent spins, it is simply all peaks should be of equal intensity. Okay, it goes by 2 to the power of n. Does it answer your question?
Thank you, sir. Thank you for such a wonderful session. I now request Professor Ramakrishna Damle, sir, Department of Physics, Bangalore University, to propose the vote of thanks. Over to you, sir.
Good morning, Professor Surya Prakash.
Oh, good morning, Professor Damle.
Yeah, before I propose vote of thanks, I just want to ask one or two quick questions.
Please.
See, these multiple quantum transitions should have been more sensitive than single quantum transitions, right?
No, it
there
is
should be a sensitivity enhancement.
No, multiple quantum is less sensitive. In fact, as the multiple quantum, what happens is, as you go to higher and higher quantum, the sensitivity keeps on decreasing. It goes by the power of the quantum. For example, single quantum is more sensitive than double quantum. Double quantum is less sensitive by. So triple quantum is even
quantum
less
of energy. Quantum of energy involved is more, right, in a double quantum transition.
No, but the allowed transition is very limited. Only one will be there. Highest quantum, if I take, let us say n spins are coupled, nth quantum only one possible transition. So sensitivity very, very low.
Okay. One other quick question. What is the particular advantage of determining the sign of the J coupling?
Okay, this is a very good question. For example, just now I told you the sign of the coupling is very important in getting the hydrogen bond. Otherwise, if the sign was wrong, I was unable to get the hydrogen bond information. Okay, that's one thing. In biological NMR spectroscopy, what people do, they detect what is called nitrogen. They look at nitrogen, fluorine, carbon coupling with proton. They align the molecule in a weakly aligned liquid crystal media, and get the dipolar coupling. When the heteronuclear involved, if you go by Hamiltonian, you will find that Hamiltonian, it so happens half diagonal terms goes to 0, and when you diagonalize the matrix, you will have only a factor of J coupling plus dipolar coupling comes into the picture. In which case, there are two parameters in a single equation. You can do whatever the value of J you take, correspondingly the dipolar coupling changes and the spectrum remains unaltered. If you do not know the exact sign of the J coupling, your dipolar coupling sign could be wrong or strength could be wrong. If the dipolar coupling strength is wrong, your detection, dipolar coupling is related to distance information. It gives you distance between two interacting spin. That will be wrong. Then your geometry will be wrong. The sign of the coupling plays a dominant role in many, many applications. It is very important. In fact, in the conventional NMR spectroscopy, most of the chemists, they don't bother about sign. Their job is simply, they don't understand why, which spin is coming, how many spins are involved, everything. Their job is, I have synthesized a molecule, whether I get the spectrum which is matches with my molecule, that's all. But when you want to get the real information like this, sign of the coupling is very important.
Okay. Okay, we all know that NMR spectroscopy is indispensable for chemistry research and research in life sciences. Professor Surya Prakash has very nicely educated us how we can resolve complex NMR spectrum and study spin dynamics through multiple quantum transitions and zero quantum transitions and so on. And in fact, I just want to tell you that while I teach NMR to my students, I just stop and say that the zero quantum and multiple quantum transitions are forbidden, and however it can be observed under special situation. I just stop that, but now I have to re-educate my student that there is a lot of things you can study if you observe multiple quantum transitions and all that. So I thank Professor Surya Prakash for sparing his time and joining this meeting and then giving a very excellent talk on NMR spectroscopy and spin dynamics. Thank you very much.
Thank you. So I can log out? Bye, Tamle. See you.
Okay, bye. Nice.
So I have to go to the department now. I log out.
Okay, okay.
Thank you, sir. Thanks for coming, actually. Malavika, you are here?
Yes, sir, I'm here, sir.
Yeah. Next speaker is Maurya. Professor Krishnamurthy will introduce.
Yes, sir.
Maurya, sir, you have logged in? Yeah. Good morning. Welcome you, sir. Unmute. Okay, fine. Yeah, in a fraction of a second, our convener has got some internet errors, actually. He is rejoining. We will continue the session. Krishnamurthy, unmute yourself. Unmute, Krishnamurthy. Malavika, madam, you proceed. Krishnamurthy will introduce the speaker.
Yes, sir. Shall I start, sir?
Yeah, please.
I now request the convener of this conference, Dr. Krishnamurthy, sir, Professor of Chemistry by University, to introduce Professor M.R. Maurya, sir, Dean, Faculty of Affairs, IIT Roorkee, Uttarakhand. Over to you, sir.
Yes. Good morning to you all. Good morning, sir. Manar Maurya, sir.
Yeah.
Yes, sir.
Can you allow me to share my screen?
Yeah, we will, sir. I will introduce you. Yeah, please.
Sure.
Yeah, you will be allowed, sir. So I will introduce you first. So it gives me an immense pleasure in introducing the speaker of today's current session. That is Dr. Manar Maurya, Professor of Chemistry from IIT Roorkee. So Professor, he's a very distinguished professor. So I would like to introduce him in brief. So Professor is basically from Jaunpur, Uttar Pradesh. He did his BSc in Gorakhpur University. He did his MSc from Bundelkhand University, Jhansi. He did his PhD from an NIT Kurukshetra. So after that, he did his postdoctoral research at several places During 1987 to 1989, he did his postdoctoral research in Loyola University of Chicago, USA. So during 89 to 91, he did his postdoctoral research in Iowa State University, Ames, Iowa, USA. Then from November 1991 to June 1993, pool officer, worked as a pool officer in CSIR lab, National Chemical Laboratory, Pune, NCL Pune. Then he has nearly 27 years of teaching experience. He joined as a lecturer in the year 1993 and he served up till 1996 in University of Pune. Then he became assistant professor in the year 1996 and he served till 2004 in University of Roorkee. Then he served as associate professor from 2004 to 2008 in IIT Roorkee, and he became professor in 2008 and he is serving as a professor till now in IIT Roorkee. So professor is a distinguished researcher. His research interests are structural and functional models of haloperoxide enzymes, vanadium complexes relevant to biological systems, vanadium and molybdenum complexes as catalysts in organic transformations, etc. So professor has completed several research projects, major research projects funded by several organizations from India. Then he has guided for 26 PhDs and there are about 5 more under his guidance. And he has published about 157 research papers in very reputed peer-reviewed national and international journals. So, and professor has delivered more than 30 invited talks at national and international levels. And he is a member of several boards, several committees, and he is member for several associations, and he has served as a reviewer for several reputed journals, and he has editor for several books. So like this, if I go on telling his biodata, it will be very long. So with this brief biodata, I request Professor Mannar Ram Maurya to deliver his talk. So over to you, sir.
Unmute yourself, sir, please. Maurya, sir.
Maurya, sir, please unmute. Yes, sir.
Yeah, fine.
Yeah, please allow me to share the screen.
Okay, sir, please. Go ahead,
Yes,
sir.
sir.
Is it visible, sir?
Yeah, it's visible. Go for full mode view.
Yeah, going for that.
Yes, perfect, fine.
Okay, good. So good morning to everyone. Myself, M.R. Maurya, and thank you, Krishnamurthy, for introducing me. It's nice words for me. Without, how much time do I have? I would like to definitely know.
Yeah, you can take, try to finish by 30 plus 30 minutes.
30
Okay.
minutes, maybe a few minutes for discussion.
Yes.
Okay, all right, okay, thank you. So the the topic I have given is development of vanadium coordination chemistry inspired by enzyme haloperoxidases. This chemistry I've been doing for last 20 years, I would say 21 years. Why this vanadium chemistry actually fascinated me, that is definitely one of the enzymes, that's one. Another thing is there different wide applications. When you look at the earth, when it starts from the biological properties were known earlier, the therapeutic applications, then the haloperoxidase came into picture. That is then the model character like structural and functional models, and then go to the catalytic applications. So when you look at the haloperoxidases, then so far 3 enzymes have been isolated from basically when you look at then it's brown algae, red algae, and fungi, and the names are given here. I'll not go by the name, just like to show you what is the real structure available for this one and from where they are coming from. Okay, and see here the structure of the enzyme, which was solved in 1996, and since then people got interested in it. What is so good here in this case, that is the vanadium center in this case. And we look at the vanadium center, we have a vanadium where one of the amine, the histidine moiety is coordinated, others are actually basically the hydrogen bonded one. And the beauty is that the all three haloperoxidases, two of them structures have been solved and combined here for your comparison. When you look at, they have a perfectly similar structure, not much structural change in both of them. Okay, and the other things that the amino acid homology are present there in all these three, and they have almost a similar structure in the active site. And the beauty is there that all of them having trigonal bipyramidal structure. Something happened wrong. Are you able to listen me, please?
Yes, sir. Yes, sir.
Okay,
You
so
are
I'll
audible. You are audible. Please go on, sir. You are audible.
Okay, so what I'll do that, I'll just go through this way, something suddenly crashed down. Okay, so I'll see that if I can do something. Okay, so I think I'll go by this one only. Please forgive me that. So the chemistry, the structure when it was established during that period, even before than that, these two people, Ron Weaver and Henry actually Hans Wilter, they were doing the chemistry on that haloperoxidase. So this fellow who was working on that crystal structure, trying to solve it, he proposed that the vanadium 5 center is present, and the Ron Weaver rushed into the lab, and then he looked at, is the really vanadium 4 or vanadium 5? So he was not getting EPR signal, but when he reduced this vanadium 5 center to vanadium 4, he could get very nice EPR spectrum of that. Then immediately they came to the conclusion that yes, that is actually vanadium 5 center, and these are the species which are responsible for that. Okay, so anyway, when the structure was published clearly, that definitely showed that that is vanadium 5 compound, and when they do the catalytic activity, then the formation of peroxo species, they proposed that it was proposed by the studies, and then the other thing, what was related to this one, that these enzymes show oxidative halogenation in the presence of halide and oxidant like H2O2. They also show sulfoxidase activity where sulfur can go to the sulfoxide and then can go to the sulfone. Further, it was very, conclusive evidence that once we remove the vanadium center from the haloperoxidases, then there is no catalytic activity. But after restoration, after putting the vanadium back, the catalytic activity were restored. Further, it was shown that they can have a VO2, VOH group, vanadium hydrate oxo compound, oxoperoxo species during the catalytic activity. These were some postulations that by different studies that it was shown that they can have it. So the question came, what would be the good models to show all these structural and the functional property of these compounds? Then answer is definitely the vanadium complex. Okay, and so during the 1998, we were going through the literature, and idea was that how to do the vanadium chemistry. That was basically my aim during that period, because I was really inspired by these enzymes. So we're looking at the how, looking at the methods, how to prepare these complexes. Okay, so ultimately the idea came and we started doing some chemistry here, and I'd like to show you that. I'd like to see, I'd like to show you that, say, we started with a very, very simple system where we took the simple vanadate prepared from vanadium pentoxide. And if you look at this ligand, the ligand is nothing but the sulfaldehyde reacted with one hydrazide to form the hydrazone, and this is potassium salt. So this is water soluble. This was made water soluble by dissolving in a potassium hydroxide aqueous solution. And after mixing, when you maintain the pH 7.5, we got a very nice orange color compound. And by different studies, we observed that this is the diaxo compound. Now, suddenly, during the next step of repetition, that I would say that you are doing that, and somehow, see, the pH was maintained by pH paper, simply no other way, because we were beginning of this research and a new lab here at IIT Roorkee, then University of Roorkee. And then by maintaining with the pH paper, certainly pH has gone down to say around 6.5. Then the color, actually the orange color gone little bit darker side. We thought maybe the same compound, but during crystallization, we observed there are two compounds which separate by the fractional crystallization. This compound actually came as a dark red crystals, which was poor soluble, and this came as a water soluble, so that took longer time to isolate it to orange color. So we separated it. Of course, we could see that the differences for those in the IR spectroscopy, and we try to characterize them. Then we thought that this actually the precursor of vanadium where we'll look at, and where the target was to prepare a vanadium 5 compound. In the first step, when we are trying to see that this reaction in the regular methanol under nitrogen as expected, vanadium 4 species, that is starting precursor, and ended up with vanadium 4 compound was expected. But when we oxidize this compound for about 24 hours, just passing oxygen from in the lab by just a simple air passing through the solution, then we observed this light greenish yellow color slowly became to dark red color. What we observed during the reduced pH, the little bit less soluble compound. So the similar color are this, and by comparing these two, we could see that the compound is the same what we observed during the fractional crystallization. All right. When we are recording 51V NMR, this is the help taken from a Germany collaborator. During recording of this potassium salt 51 vanadium NMR, what we observed that in the beginning with fresh sample, we could get one very nice 51 vanadium NMR peak around minus 540.5 ppm. But keeping this solution for about 4 or 5 days, then another peak started growing at this point. So that gave us some clue that something going on in the solution. We kept this solution in the lab for say more than 15 days. And what we observed that one compound, light orange color compound, in fact, precipitated out, gave a nice crystal. So we tried to solve it through some collaborator, of course, because the facility is required to. And we observed that there is a structural change here where we have a deoxygenation process, and we got this is a related compound.
Sir, namaste.
So what happens during that? This is, you see, oxo group transfer has occurred where methanol has taken care of this, remove this oxo group, and we can say methoxo group at this point. So that was a good observation at that point, and we could see that then it was really exciting that the vanadium chemistry, what we planned, is working out. Now, taking that potassium salt of this diaxo species, because this was a water soluble, So we thought, okay, let's put some more acid to reduce the pH of this compound and see if we get the same compound we observed after reducing the pH about 6.5. To our surprise, that compound one immediately precipitated during the titration with dilute HCl, okay, in the water solution. This compound precipitated, and this gave entirely different IR spectrum, where we could see two nice peaks around 3000 coming, and we had no clue why this coming. Only we could guess it. This is coming possibly due to the NH peak, NH proton, what is expected in that region, or the water. We never expected water in this case. So there was no clue basically what other than that where this proton is coming, where it is protonated. Then during the same period, one paper was published in Journal of Inorganic Biochemistry where they have shown that the nitrogen of the hydrazide moiety can be protonated if you reduce the pH. And then they saw the crystallicity of this one, and that gave the nice clue that that is definitely the hydrazide moiety, that is azomethyl group, that is protonated. All right. So that was a really nice thing. And then we could definitely conclude this the same way that this is the hydrazide moiety protonated. We also worked that. So we found the clue that we can do this chemistry, and by this way, if we can isolate this potassium salt, so if you titrate it, we can get the nitrogen protonated. And the beauty of this one is that, see, what I have shown here, that is a dinuclear species. If you keep it in methanol for a month period, then slowly it converts into this oxomethoxo. While this dioxopotassium salt, it can go to the methoxo within a week period. However, this one, if you dissolve in methanol, this goes to methoxo species within 24 to 48 hours. And this methoxo compound, if you keep in acetonitrile for a week period or reflux it, say about 24 hours, slowly this converts into dinuclear species. So we could make a very good cycle, and we could observe all these, and we will publish this, our observations. Now, the idea was there to prepare a structural model of hydroperoxidase, where, as I mentioned in the beginning, there is one histidine coordinated to, and we were thinking to design the ligand first. We thought, okay, let's design this kind of, see what is this. Basically, this is coming from the sulfaldehyde acetylmethyl benzimidazole. Okay, the ligand preparation is so easy. So we try to react this one with vanadium acetyl acetonate. As expected, we should get vanadium 4 compound. In fact, we got vanadium 4 compound. We characterized that this was related to one of the acetyl acetone unit is still attached to this one, and we got this octadal compound with a relatively good magnetic moment. What is expected for that? And we keep the filtrate SI, and we just kept it for and washed it slowly. You have to observe that from the filtrate, we could get this compound, orange color compound, precipitated. And again, we filtered this compound and kept this filtrate again for a week period. Then we could get a green color compound, and later we analyzed this one. This compound has some impurity of this dioxo compound, so that could be separated because this is insoluble in dichloromethane. This material is soluble in dichloromethane, so we could separate out and we could crystallize them nicely. Other thing is that if we put in a solvent and pass oxygen, then this compound to be converted into the dioxo completely. That is expected, and that gives a very nice 50 and vanadium NMR at 567 at the negative point. So could characterize it. So within the one reaction system, we could get 1, 2, 3, and 4 compounds, and that was the beauty of this reaction. But the patients actually kept us to observe this kind of reactions. Okay, so what happens? Why we are getting this compound, the diaxo, where this is one of the acetyl acetonate unit. If I go back and show you one of the acetyl acetonate unit, and here you have a basically the ligand derived from sulfur dihydral orthophenylene diamine, where this is coming from. So basically, this is coming from the decomposition of this compound. This 2-amino methyl benzene group basically is prepared from the orthophenylene diamine. Okay, and that orthophenylene diamine, you will see that is broken down here. How this is broken down? This is breaking down into giving the orthophenylene diamine, and this also partly reacted with, because this is broken down, reacted with the sulfaldehyde to giving sulfaldehyde orthophenylene diamine ligand. Because here this is partly sulfaldehyde is available after breaking down the ligand and this amine basically. Okay, and this amine moiety 2-amino methyl benzimidazole reacted with the vanadium precursor to give this compound. So the thing very slowly clear that we are getting the decomposition. We are seeing the decomposition of the solution, and this compound we are getting. So the question was, can we get this compound by directly reacting this along with the vanadium precursor? We tried to do that, and to our surprise, we got the same compound where this actually reacted with condensed at this point, and then we got the compound, and then that also gave the 15 vanadium NMR very nicely. And we could characterize all these compounds by X-ray crystalloscopy also. So I'm not giving you that X-ray structure of that compound because of this time limit. Then we also look at the same way with the other compound, and this is with the 2-amino ethyl benzimidazole. In this case, we definitely observed these similar types of pattern, but the decomposition was relatively much slow in this case. So we could observe two different types of complex formation by oxidizing it, and this one, but we could not form, could not prepare that compound which came after the decomposition. Okay, and then try to see the reactivity of this compound with oxygen. It is going to diaxo, but when we take the H2O2, then it responds very nicely peroxo compound. By IR, we can characterize them very nicely because here we have an oxo group and we have peroxo group. So these three peaks are into peroxo species. We can characterize after isolating them. And also, I'll show you here some of the IR spectra where this is for the orthophenylene diamine. Very nicely, it gives peak as 981 in the IR. When we go to the diaxo, we could get two peaks in that region, 900 region, with symmetric and asymmetric diaxo group. And if you go to peroxo, then only one nice peak in the oxo region, then the peroxo signals coming at this point all are identified and have been assigned that. Okay, so this way we could prepare very nicely a good structural model of the haloperoxidase. The reason is why, because if I go back, I'll show you that this compound has a very good trigonal bipyramidal type of structure. The same way the other species also the similar one, and we could very easily say that we have prepared a beautiful model of structural model of haloperoxidase. Definitely the vanadium compounds inspired by the haloperoxidase. And the other compound we could also prepare here by changing this one with this NN, dimethyl ethylene diamine, and we could oxidize this acetyl acetonate to another trigonal type of complex, which is another good structural model of haloperoxidase. Then, say we change this side here. instead of sulfaldehyde, we have taken here pyridoxal moiety, where you have a nitrogen in the pyridine, nitrogen in the ring system, that is the pyridine moiety, and also you have the hydroxide moiety. Again, the reaction was carried out in water, and after maintaining the pH at 7.5 of the reaction mixture, we got orange color compound, but during fractional crystallization, we could separate these two compounds. Again, is the major what is coming at the potassium salt of the diaxo compound, and the minor compound you could also observe, which showed diaxo peaks very close to that, but other observation was distinguished from this to this one is that protonation of the nitrogen. Now the question was, earlier we observed in the very beginning that protonation occurred at this point, and we proposed that protonation occurred at this point, but however now in the presence of this ring where pyridinic nitrogen available, this is the preferred one, and currently that also can be proved that this will be the preferred over this hydroxide moiety, and so possibly the nitrogen protonation and peak in the IR coming due to this one. Now, so we try to do the same chemistry, like in the presence of H2O2, can we go to the diperoxo species? Yes, we can go to, and even we prepared in the simple water system the same peroxide compound by taking, say, this potassium vanadate prepared from vanadium pentoxide. Then you add H2O2 to in situ generate peroxide species, react with the potassium salt of the compound, and can go to peroxo compound formation, which can also be monitored in the solution by titrating the diaxo species with the H2O2. You can see the very nice change in the this band around the UV visible band by due to generation of this peroxide solution. Okay. Now, what we have done here, we have taken the pyridoxal moiety and then changed to S-methyl dithiocarbonate and S-benzyl dithiocarbonate. We are now oxygenizing change to sulfur, and then when we carried out this reaction with the precursor, this and oxidized by aerial oxidation, we observed this compound a neutral species diaxo. Though we expected the dinuclear V2O35, like earlier we have done that, but no, this is stabilized as a diaxo neutral mononuclear species with this protonation of this compound. And also, by using our water method, potassium vanadate and the ligand dissolve in water by using potassium hydroxide, maintaining the pH 7.0, we observed only this compound. We did not observe potassium salt of this compound. Also, we tried another method. What we have done here that this vanadium 4 acetyl acetonate, we oxidize first in the presence of air by stirring, say, for about 24 hours, where the light blue color changed to complete yellow color, then reacted this one, which we could in a single step go to this one. So all three methods basically ended up with the neutral diaxo species, mononuclear one is, and this was like a contrary to our imagination and observation. We should get here V2O3 type or potassium salt, but we did not get it. So to prove it, we definitely try to grow the crystal of this one, and you will see that here the nitrogen is actually pyridine nitrogen is protonated, not the your azomethyl nitrogen, what is should be at this point. Okay. And the same way in this one, other example of the same series, you find that this nitrogen was protonated, and that was the reason we could get the neutral diaxo species. And that actually now, then we could immediately tell that if we have a pyridinic nitrogen available and you have a hydrogen moiety available. If you do the protonation or when you titrate with HCl, you will end up with this one first, then you can go to this one if furthermore acid is available. Now, to develop further chemistry, we have taken the same hydrogen moiety and we have taken here now the acyl pyridine and prepared the ligand. Now, method is well established. We got the idea how to do that. So, we reacted with acyl acetonate and in the nitrogen we could get the another compound. Where the total compound is one acyl acetonate coordinated because here it is system is now monobasic tridentate system. So this is stabilized like this way again, and you could see that a very nice magnetic moment observed for this compound. But again, on oxidation, we could get the simple dioxide species. Here, this is the started tetragonal pyramid compound because tau value is about 0.37, which is coming to about say 1 R0. Okay, then definitely one can say that is a square pyramidal type of or tetragonal pyramidal type or the trigonal bipyramidal type. Okay, but in other case, see, two of the system here when this R is like isonicotinamide, like the para position the nitrogen here and the benzene ring, you could get a mononuclear species after crystallization. But in this case, where you have the meta position and the furan group, then you could get this kind of compound. But thing is that these two compounds are when dissolved in solution, they behave as a monomeric species. So when you look at here, cut it from here, you will get two monomeric compounds. Okay, so we could very easily prove that in solution they are mononuclear, and when upon isolation, you can go to the dinuclear species or just I would say the dimerization. So and no, I mean any other chemistry involved, simply dimerization, you could see everything what is expected for the mononuclear species. Okay, so these two are the mono and dinuclear species structure that is proved by crystal structure. Now here, see how chemistry is changing. Again, we have taken here sulfur in place of oxygen. Chemistry is exactly same. No difference in this one. And you could go to very nicely to obtain the trigonal bipyramidal type of compound for this ONS donor. And further, you could check it by the single crystal X-ray study. So I was telling that here, the two types of things are possible in this kind of structure. One is the tetragonal pyramid and trigonal bipyramidal. So if the tau value, which is actually one can calculate through these bond angles, if this is 0, then it's definitely a tetragonal pyramidal compound, but if tau is equal to 1, then it comes to the trigonal bipyramidal. You see what is the different structure is when we consider this NVS angle and N1VS and nitrogen, vanadium, oxygen bond. Okay, so this way we could show that. See here, this is value is coming 0.47, and that is actually means this is discarded towards right. Whatever you say, either you say trigonal, bipyramidal discarded towards tetragonal, or tetragonal discarded towards the bipyramidal is coming within halfway from the both sides. Now, this was very interesting. See, I mentioned that earlier that this we oxidize really overnight in one case, and we could prepare the compound with the diaxo compound. Now here we thought if this is we are oxidizing, then we should have this BO2ACH2 because vanadium 4 oxo is going to diaxo. So can we isolate this, or can we use or make it like a potassium salt? So we added KOH, because then this way the oxidation state and neutrality is maintained, the ionic charges, and then when
Excuse me, sir. Can you summarize in another 5 minutes?
yeah, sure. Okay. So
Sorry.
yeah, sure, no problem. Okay, so what we observed that here, reacting to the same ligand, we could get entirely different compound. Here we expected, say, acetyl acetone, right? But this is not acetyl acetone. We look at this methyl group is replaced by the oxygen. Where the clue is coming, where this is coming from? See here, this is structure. And then we propose that the base assisted oxidation, actually a transformation of the acetyl acetone is coming to this malonic acid type, and we are getting the final compound. So we extended this study now to the dinuclear compounds. See here, this is a sulfide is bridged to the methyl group, and then we did a lot of chemistry, and these are the structure to show that. Okay. And then I'll show you some more thing here that we tried to do titration with H2O2 and recorded treatment vanadium NMR, and you could very nicely see that the dioxide species is going to the peroxo. We could see the nice peak, but if we keep it the solution for a very long period of time, then you will see that again this peak is going on, completely gone at this place, and then going to the generating this species. All right. And we extended the species with the different types of the reagent, the different types of compound, and we could characterize that. Okay. I wanted to show you one more thing here that this one, we extended this chemistry to the many type of ligand. We designed this kind of ligand. Okay. And we try to do the similar kind of chemistry, and you will see that with taking with the one ligand simply by reacting with acetyl acetonate in the acetonitride, giving you the expected compound. When you react with vanadium vanadium sulfate in ethanol, this gives to the diazo compound. In acetonitride, it could give you the V2O3 type of species. This compound acetyl acetone coordinated, where one arm is not coordinated to the vanadium center. When you steerate acetonitride, that gives you the very nicely V2O3 type compound where this pyridine nitrogen is coordinated. And if you steerate in methanol, since this acetyl acetone coordinated, it can go to the methoxy compound. But again, this nitrogen is not coordinated, and we keep in acetonitride for a longer time and heat it, that can go back to it. Okay, so a lot of chemistry we could generate from this one. And not only that, we characterize by all means, and then we try to do the oxidative bromination, that is haloperoxidase activity, what is carried out by the haloperoxidase enzyme. And you will see that this experiment was done by a simple MSc student where sulfaldehyde has been brominated to 5-bromosulfaldehyde in a major yield along with some other yields, etc. Using this simple vanadium compound, what we expected to do them, and in fact we could observe it very nicely. Even we have done the oxidative bromination of, say, styrene, and we have done oxidation bromination of the other and sulfoxidase activity. What all we have studied that. Okay. And we have also done some oxidation of the sulfur containing compound. Different. So that's all I have to say at this point. And then at the end, I would like to definitely thank the organizer to giving me opportunity. And of course, DST and CSR for a lot of funding. But at the end, if I summarize that, then I would say that a rich and interesting chemistry of vanadium has been developed. Of course, that is inspired by haloperoxidase enzyme, and they could become a good structural model as well as good functional model of those complexes, because catalytic ability that is showing very nicely to the different ionic transformation. So thank you very much for listening my talk, and if you have any question, then I can definitely take up. So,
Malavika?
Yes, sir.
Yeah, you can ask questions.
If the participants have any questions, either send it in the chat box or unmute yourself and ask the question directly.
Yeah, if any question, definitely I can take up. Something system has gone wrong. Suddenly, something happened. So I'm not able to actually come up to the screen. Let me see if I can come. I'm not able to see that. Okay. So something has
Anyone
gone
has any
No,
question?
Sir,
Any question, please?
sir.
Yes.
Yeah, I'm Krishnamurthy only.
Uh-huh.
I think if there are no questions, I want to ask just one question.
Yeah, sure.
Yes, sir. With this vanadium complexes, can we make this vanadium complexes in 3D form, like vanadium metal organic famers like?
Oh, yes, you can go and see. You have to select the ligand. That is very important. Okay. If you select the correct ligand, okay, then definitely you can go to metal organic framework. There will not be any problem. Okay. The thing is only the selection of the ligand. We are interested in the simple molecule so that we can at least characterize and understand the vanadium chemistry well. But yes, even some examples are known. You can go that. Only problem one will face that because in a regular say metal like copper, nickel, cobalt, etc., there is no oxo group. In this one you will have an oxo group. Okay, so designing will be a little bit difficult and that will be a challenging. But yes, if someone designs and characterizes it well, definitely I'm sure they should be able to do that. Okay.
Thank you, sir.
Yeah.
Yeah, there is something in the chat box. Malavik, can you please check?
No, sir, nothing is there, sir.
Okay. So if there are no questions, so I take this opportunity to thank Professor M.R. Maurya, sir, for having delivered a very interesting and very important topic. So because the complexes are very important compounds, chemical molecules, so they play a lot of roles in biological field, in various fields, especially as catalysts for various applications, synthesis of several molecules. So he has explained nicely by taking simple precursors of vanadium, by taking some of the simple salts, and by playing with the solvent like methanol and oxidation by exposing to air, then by changing the pH of the medium, so getting very interesting vanadium complexes which are of very interesting structures. So thank you so much, sir, such a wonderful talk. Definitely it will be useful for all chemistry people. So thank you once again for such a nice talk, sir. Thank you so much, sir.
Thank you so much. Yeah.
Yes, sir.
Have a nice day, all people.
Yes, sir. Yes, sir. So yes, sir. Bye-bye, sir. We'll be in touch, sir. Thank you.
Yeah, sure. Very
Yes.
nice.
So I take this opportunity to thank all the professors like Vijay Kumar Dodmani sir, Nagaraj Kampsali sir, and who are all involved here in conducting these parallel sessions, common sessions especially, and mainly Malavika for having compiled the programs since 3 days so nicely. So thank you so much for all your involvement and committed work. Thank you. And for all the rest all who are all involved in conducting these common session programs, thank you one and all. And one Malavika, final this one from your side. Yeah.
Yes, sir. Thank you for the opportunity, sir. And I now request all the participants to kindly join your parallel session.
Yes.
Malavika once, thank you for the Krishnamurthy for chairing the session and conducting the session in a very nice and attractive way. Thank you,
sir.
Thank you, Professor Maurya, sir, for giving an excellent talk. We'll end the meeting.
Yes.
All participants are requested to join for the parallel sessions.
Yes, sir. Thank you.
And the common channel will be by valedictory
Yes,
Yes,
sir.
sir.
Once again, yeah.
by 4:30.
I
Thank
request
you.
all the participants to join by 4:20 so we can continue with the validity in the sharp timings.
Sure.